In this video, we are going to solve a problem using a hypothesis test. Starting with the directions, they say write out the solution, including all 4 steps listed here. Step 1 says state the hypotheses HO and HA, that is the null hypothesis and the alternative hypothesis. Step 2 says calculate the appropriate test statistic showing your work. At minimum, write the letter of the test statistic, the formula, the numbers filled into the formula, and the final answer. Round to 2 decimal places. Step 3 says decide whether or not to reject HO, state what happened to HA, and it says for this step, show both the p-value approach and the CV approach, the critical value approach. Step 4 says interpret the hypothesis test in terms of the original question. Be sure to reference the significance level in your interpretation. Answer the question, is there evidence that the customers at these new locations are waiting longer than the maximum mean time dictated by the retailer? Should action be taken based on the results? The problem states, a chain retailer has target service levels that each location is expected to deliver. The target established for customer wait times at checkout is 210 seconds or less. The retailer opened a new location called store number 156. The analyst is once again tasked with testing wait times at the new store. This is the second in a series of problems. Any store found in violation of the 210 seconds or less standard must take action to reduce waiting times. The analyst took a random sample of 34 customers at store number 156 and measured the time they had to wait to check out. In the sample of customers, the mean waiting time was 231 seconds. Drawing on past experience with checkout times at this retailer, the analyst assumed a population standard deviation of 86 seconds. Perform and interpret a hypothesis test to determine whether the population mean waiting time at store number 156 is longer than 210 seconds at the alpha equals 0.05 significance level. Is there evidence here that store number 156 needs to take action to reduce waiting times? Every hypothesis test is about a population parameter, and this one they are asking about a population mean. So the parameter they have in mind is a population mean, and the question they have is this mean longer than 210 seconds? That question leads us to a hypothesis test about a single population mean. Because that question, whether a population mean is longer than 210 seconds, aligns with one of the 3 questions that the hypothesis test for a single mean can answer. The upper tail test for a single population mean answers the question if a population mean is higher or greater than or longer than a given number. So in this case, we can use an upper tail test for a single population mean to answer the question that this analyst has. In order to actually formulate these hypotheses, we need to identify the number mu0, which goes on the right-hand side of the hypotheses. And in this case, that is going to be 210, because that's what they want to know. Is this population mean mu longer than 210? And that is actually what the alternative hypothesis says in words in the upper tail test. So writing the hypotheses according to the formulas here, we see that HO, the null hypothesis, is mu is less than or equal to 210, substituting in 210 for mu0, and HA is mu is greater than 210. So if we can reject the null in this and prove HA, that's when we will know this store has lines that are too long. Now let's turn to step 2, which is choosing and calculating a test statistic. This particular hypothesis test, the test for a single population mean, has a choice of 2 test statistics. Choice 1, if the population standard deviation sigma is given, calculate z-test. And choice 2, if the population standard deviation is not given, calculate t-test. In that case, you would be using the sample standard deviation instead. So which standard deviation are we given in this problem? In the last sentence in the second paragraph, it says the analyst assumed a population standard deviation of 86 seconds. So population standard deviation is notated with sigma. This means sigma is given or known because it's known to be 86 seconds. So sigma equals 86 in this problem. And that means we're going to do a z-test because we have a value for sigma. Let me be sure to put that in the notes so that you know why we made this choice. So the z-test statistic follows the formula you see at the left. Z-test equals x bar, which is the sample mean, minus mu zero, which is the hypothetical population mean from the hypotheses, divided by sigma, divided by the square root of n, sigma being the population standard deviation and n being the sample size. Now we've identified mu zero and sigma, but we don't have x bar or n yet. But we see in the problem that in the sample of customers, the mean waiting time was 231 seconds. So the mean of a sample is notated with x bar. X bar in this problem is 231. The final piece of information we need is sample size. It says the analyst took a random sample of 34 customers. So 34 customers, that's how many members of our population are in the sample, and that is what we call sample size. Now we'll substitute in our values for this notation. 231 is x bar minus 210, which is mu zero, divided by sigma, which is 86, divided by the square root of n, which is 34. We're going to calculate this in Excel. And in order for it to calculate correctly, we have to put parentheses around the top and around the bottom of this fraction so that the subtraction on top will be done first and other things and everything will stay in order. So in Excel, to calculate this, it would be equal sign, open parentheses, 231 minus 210, close parentheses, divided by, so division sign, open parentheses, 86, divide square root, SQRT, open parentheses, 34, close parentheses, close parentheses. Hit enter, and we have 1.423837 to 2 decimal places. That rounds to 1.42. So now we have our z-test statistic, which is 1.42. Having completed step 1 and step 2, I'm going to move to step 3. So I've changed the references on the left-hand side to our step 3 rejection rules. Because step 3 is the step in which we decide whether or not to reject the null hypothesis. There are some pieces of information we need to execute this step. One is, what is the alpha significance level that we're using in this problem? And we see from the text of the problem that alpha equals 0.05 in this problem. So that is the significance level we are going to use. The next thing to decide is what distribution we're going to use for our p-values and critical values. And this is a z-test using a z-test statistic. So we will use the z distribution to grab the p-value and the critical value for this test. I'm going to start with the critical value approach this time. It doesn't matter which one we start with, so this time I'm going to do critical value approach first. So the rules we'll be following are these, and we need to look up the upper tail critical value for this alpha significance level. And since we are using a z-test statistic in this test, it's an upper tail critical value of z that we need at alpha equals 0.05. So that is to be found on the z table. Head over to the z table, to the critical value inset in the upper right-hand corner. Alpha is 0.05, which means we have a critical value of 1.645. We leave it positive because it's an upper tail critical value that we need, and upper tail critical values of z, like all values of z, are positive. Let me just note the alpha significance level we're working with, 0.05, and the fact that this is an upper tail test, because that's important for this step to know which rules to follow and what alpha to use. We have the critical value. we can apply the rule. If the test statistic is greater than or equal to the upper tail critical value, reject HO and accept HA. Otherwise, do not reject HO and HA is unsupported. So our test statistic is 1.42. Our upper tail critical value is 1.645. But I am going to do the diagram, the rejection diagram that implements this rejection rule. The rejection diagram starts with the distribution. The upper tail rejection region is here because this is an upper tail test. The boundary of that rejection region is the critical value 1.645. It is the value of Z that has 0.05 probability to the right. What 1.645 is the lowest your test statistic could be that you would still reject the null hypothesis. That's why the range of Z's to the right of 1.645 constitute the rejection region. If our Z test statistic goes into the rejection region, we would reject the null. Here, our test statistic is 1.42. 1.42 is less than 1.645. It does not belong in the rejection region, which is only where Z is greater than 1.645. So here, because 1.42 is less than 1.645, we do not reject the null hypothesis. That means the alternative hypothesis is unsupported. We would only reject HO if the test statistic was greater than or equal to 1.645, and here it's less than, so we cannot reject the null. When we cannot reject the null, that means there is no evidence in favor of HA, which it means that HA is unsupported by the evidence. Now that we've covered the critical value approach, let's take a look at the p-value approach. So the p-value approach rules for an upper tail test, of which this is one, are given here. And it says, look up the upper tail p-value of the test statistic. Now the test statistic in this case is z-test, which was 1.42. P-values for z-test statistics are on the z-table. Here's the z-table. Through the first decimal place, it's 1.4. The second decimal place is 2, so that gives us the 0.02 column. So the upper tail p-value for z equals 1.42 is 0.0778. So the upper tail p-value is 0.0778. And with that and the alpha of 0.05, we can apply the rejection rule. We compare our upper tail p-value to alpha. If the upper tail p-value is less than or equal to alpha, we can reject the null and accept HA. But in this case, our upper tail p-value is greater than alpha. 0.0778 is greater than 0.05. So we're in the otherwise condition. Otherwise, if your upper tail p-value is not less than or equal to alpha, you have to not reject the null hypothesis, and HA is unsupported. So because our upper tail p-value 0.0778 is greater than 0.05, which is alpha, it does not satisfy the rejection rule for the null, and so we do not reject the null hypothesis, and HA is unsupported. Before moving on to the interpretation, I want to talk about the critical values and the p-values again. Looking at our critical value diagram, what I'm shading in here is the upper tail p-value of 1.42. So the pink striped area is the upper tail p-value of 1.42. And we just looked that up and found out that that area is 0.0778. So you can see from this visual that the p-value is greater than alpha, alpha being the purple shaded area, alpha being 0.05. And we can tell that visually because the pink striped area is larger than the purple striped area. It encompasses the purple striped or the purple shaded area plus some more, so it's bigger. The p-value being bigger than alpha is exactly what happens in an upper tail test when the test statistic is less than the critical value. So if we look at it from the critical value point of view, 1.42 is less than 1.645, which tells us 1.42 is not in the rejection region. But what it's telling us really is that the p-value of 1.42 is greater than 0.05. If it was within the rejection region, the test statistic, its upper tail p-value would be less than 0.05. Here we are at the final step, which is step 4, interpreting the results. Upper tail test, and we did not reject the null, so the interpretation template is this one. At the alpha significance level, the evidence does not support the conclusion that mu is greater than mu 0. We have to fill in alpha, we have to fill in mu, and we have to fill in mu 0. But let's talk about where this actually comes from, because it comes from the alternative hypothesis. If you do it this way, you don't have to know the template because you can always read it from the alternative hypothesis. So the alternative hypothesis in this test was HA is mu is greater than 210. Mu is the population mean wait time at store 156. The greater than, I'm going to call that longer than in this case because we're talking about time. And 210 is the policy max that was set by the retailer. That was the maximum that their lines were supposed to be. So any lines longer than that on average, any customers waiting longer than that on average are in violation of the standard. But the thing about this HA is it is unsupported. We found it was unsupported because we could not reject the null hypothesis. And when HA is unsupported, what that means is there is no evidence in favor of what it says. So there is no evidence in favor of the statement that the population mean wait time at store 156 is longer than the policy max. So the interpretation is at the alpha equals 0.05 significance level, the evidence does not support the conclusion that the population mean wait time, which is mu in this case, is longer than the policy maximum set by the retailer, which is 210 seconds. So, given that there is no evidence that this store is violating the policy, it does not need to take any action. Had we rejected the null hypothesis, that would have been evidence that the store was violating the policy because that would show that the population mean wait time was higher than the max set by policy, which is 210. But here there is no evidence that store 156 is violating the policy because we were unable to reject the null hypothesis. So there is no need to take any action at this time based on this analysis. And that is the solution to this problem. Thanks for watching.